Have you ever looked up at the night sky and just wondered what's out there floating in that vast, dark expanse between the planets? We see the moon, we see the planets, we see the distant glimmer of stars, but there's more, so much more. Lurking in the shadows are millions of cosmic nomads, ancient relics from the birth of our solar system. We call them asteroids. For most of human history, they were just points of light, mysterious wanderers. Sometimes they were omens of doom, celestial harbingers of disaster. But now, our perspective is shifting. We're starting to see them not as threats, but as opportunities. They are cosmic treasure chests, just waiting to be opened. Think about it, these aren't just inert, boring rocks. They are time capsules, each one holding clues about the very formation of Earth and its neighbors some 4.6 billion years ago. They are the leftover building blocks, the cosmic debris that never quite made it into a full-fledged planet. And because they've been drifting in the cold, preserving vacuum of space, they are pristine. They carry a chemical record of the early solar system, a story written in elements and minerals. The answers might be locked inside a chunk of rock hurtling past Jupiter right now. So why go through all the trouble? Why spend billions of dollars and decades of effort to chase down a bunch of rocks in space? It feels like a monumental task, and it is. But the reasons are just as monumental. The motivation isn't a single, simple thing. It's a powerful three-pronged driver pushing us forward. The first, and perhaps most obvious, is the demand for resources. Here on Earth we have a growing population, with a growing appetite for the metals and minerals that fuel our technological civilization. From our smartphones to our electric cars, many of these are becoming scarcer and more difficult to mine. Asteroids represent a nearly inexhaustible supply. The second driver is pure, unadulterated science. Asteroids are pristine relics. They are the leftovers from the solar system's baby shower. By studying them up close, we can peer back in time. Did asteroids deliver water to a young, dry Earth? Did they seed our world with the complex organic molecules necessary for life to begin? Finally, there's the strategic advantage for the future of space exploration. The biggest barrier to a sustained human presence in space is the sheer cost of getting stuff off Earth. Our planet's gravity is a powerful tether, but what if we didn't have to launch it all from Earth? Asteroids become cosmic gas stations and hardware stores, making space travel cheaper, safer, and more sustainable. When we say an asteroid is a treasure chest, what exactly are we talking about? What's on the shopping list for a cosmic prospector? It's not all just boring rock and dust. Asteroids come in different flavors, broadly categorized into a few main types based on their composition. The most common are the C-type, or carbonaceous asteroids. Dark, almost coal black, rich in carbon, clays, and silicate rock, some of the most ancient objects in the solar system. C-types are exciting because they contain water locked in clay minerals. Up to 20% of their mass can be water. Water? We have oceans. But water in space is liquid gold, essential for life support, for drinking, for growing food, and for providing breathable oxygen. Even more, it's the primary ingredient for rocket fuel. Split H2O into hydrogen and oxygen. You get powerful chemical rocket propellant. Next, S-type, or stony asteroids. Made primarily of silicate materials and nickel iron, these metals are the building blocks for large-scale construction in space. Finally, M-type, the rare metallic asteroids, the tantalizing prize. A single large M-type could contain more precious metals than all human history has mined, worth trillions or quadrillions. So we know what we're looking for and why we want it, but how do we actually get there? The distances are immense and the targets are small, dark, and fast-moving. This isn't like prospecting on Earth with a pickaxe and a mule. The first step is prospecting. We rely on our robotic eyes and ears in the sky. Telescopes here on Earth, telescopes in orbit, Vera C. Rubin Observatory. It scans the entire sky every few nights, catalogs millions of asteroids, tracks their orbits with incredible precision. This gives us the map. It tells us what's out there. Once a promising target is identified, we send in the scouts. Small, inexpensive robotic probes, our robotic geologists, flyby missions, flybys, spacecraft zipping past, snapping pictures, collecting data. Spectrometers analyze reflected light, orbital missions, orbiting for months or years, detailed surface mapping, sample return missions, the gold standard, Hayabusa 2, OSIRIS-REx. They didn't just look, they touched. Small grams of dust and rock returned to Earth, analysis in top laboratories. Next, even more sophisticated prospectors, swarms of autonomous CubeSats. So, once you've found your trillion-dollar rock, how do you actually mine it? Well, this is where engineering creativity really shines. The environment out there is, honestly, completely alien. There's no gravity to hold you down, no air, and the temperatures can get pretty extreme. You can't just land a big yellow excavator and start digging, that's for sure. Several innovative mining techniques are being developed, each one suited for different types of asteroids and resources. One of the most straightforward concepts is surface scraping strip mining. Imagine a robotic mining vehicle that looks like a giant space Zamboni. It would land on the asteroid, anchor itself to the surface, use a rotating brush or a series of scoops on a conveyor belt to collect the top layer of regolith, and feed that material into an onboard processing unit. For more solid asteroids or deeper resources, you'll need more aggressive methods. One idea is pit mining. A mining robot would use a cutting tool or a drill to excavate a pit, a robotic open-pit mine in zero gravity. The most ambitious idea for small metallic asteroids is bag and process. You don't land, you enclose the whole rock in a giant bag. Once captured, focused solar energy heats the object, volatiles cook out and are collected, metals melt and are separated. The asteroid becomes the crucible. As exciting as all this is, we have to be realistic. Asteroid mining is hard, really, really hard. Space is an unforgiving environment. The first and most obvious is distance. The nearest asteroids are millions of kilometers away. Even with our fastest rockets, the journey takes months or years. Missions require incredible long-term reliability. There's no roadside assistance in space. A broken component halfway to the belt could doom a multi-billion-dollar mission. Communication is also a problem. The time delay for radio signals can be many minutes. That makes real-time remote control impossible. They need to be highly autonomous. Then there's the bizarre, counterintuitive environment of microgravity. A small asteroid's gravity is thousands of times weaker than Earth's. A gentle push could send a billion-dollar robot tumbling off into space forever. Even the act of digging is a problem. The force of an excavator scooping up rock would create an equal and opposite reaction, pushing the vehicle away. Any mining operation will require complex anchoring systems. Harpoons, drills nets. Let's not forget the financial and legal hurdles. These are not small-time operations. An asteroid mining venture will require an upfront investment of billions, maybe tens of billions of dollars. It will be years, perhaps decades, before there is any return on that investment. And finally, there's the simple, brutal reality of the space environment itself. Spacecraft and robots have to survive extreme temperature swings, constant cosmic radiation, and hypervelocity micrometeoroid impacts. So, you've overcome the challenges. Your robot is scraping away at an asteroid and you're collecting valuable materials. What do you do with them? One option is to bring them all back to Earth. But perhaps the most revolutionary idea is to use them right there, in space. This concept is called in situ resource utilization, or ISRU. It means living off the cosmic land. It's the single most important factor in making humanity a true spacefaring species. The most immediate and critical resource to be utilized in space is water. Water from C-type asteroids, hydrogen-oxygen breathable air for astronauts' high-performance rocket fuel. Imagine spacecraft traveling from Earth to Mars not carrying all their fuel for the round trip. They can make a pit stop at a robotic refueling depot orbiting a water-rich asteroid. This dramatically reduces the mass of the spacecraft leaving Earth, making the mission cheaper and safer. Beyond fuel, metals harvested from S-type asteroids, M-type asteroids open up large-scale construction in orbit. Right now, every space station component must fit inside a rocket nose cone and survive launch. Smelt iron, smelt nickel feed into a 3D printer or automated fabrication unit. Construct massive structures that would be impossible to launch from Earth. Giant solar power satellites, sprawling space habitats with artificial gravity, enormous radio telescopes with unprecedented sensitivity. ISRU creates a virtuous cycle. First mining missions use harvested water to refuel the next missions. Metals build bigger, more efficient mining equipment. A feedback loop bootstraps a self-sustaining industrial ecosystem in space. While using resources in space is revolutionary, the economic driver for many early ventures will be bringing high-value materials back to Earth. Specifically, platinum group metals from M-type asteroids. Their scarcity on Earth makes them incredibly valuable. But how do you get a payload of precious metal from an asteroid millions of kilometers away back to the ground safely? It's a complex orbital ballet requiring precision and patience. After surviving the trial by fire, parachutes deploy to slow descent for a gentle touchdown in a remote, pre-designated site. Recovery teams retrieve the capsule. The space mine Platinum completes its journey, ready to enter the global market and maybe change the world. When we look back at this moment from the future, we'll see the dawn of asteroid mining as a turning point, as significant as the mastery of fire, the invention of agriculture. It represents a fundamental shift in our relationship with the cosmos. For all of human history, we have been confined to this one beautiful, fragile planet. Asteroid mining is the key that unlocks the door to the vast, untapped wealth of the solar system. We graduate from being a species living on a planet to a species living in the solar system. This endeavor is about more than just money or metals. It is a profound expression of our most fundamental nature: curiosity, desire to explore, ingenuity. The same spirit that drove us out of Africa across the seas to the poles of our own world is now driving us to the asteroids. So, as we stand here today, we are the generation that is laying the groundwork for this incredible future. The asteroid belt is our new frontier, a frontier of infinite possibility. Keep looking up.